All right, okay, so in this first video as a practice, I will redo the class we did for the last time on Wednesday. So it was about the Lebesgue-Radon-Nikodym theorem. So these are the PDF notes I put on Blackboard. Let's read the statement together. So you have mu, a positive sigma finite measure, that's the reference measure if you wish, and nu, sign measure, possibly always sigma finite. Then the theorem says that you can decompose your sign measure into two parts. One is mutually singular with respect to mu, and the other one is absolutely continuous with respect to mu. Okay? So it's a good time to review these notions of mutually singular, absolutely continuous, and pause the video if you wish. And then what happens is with the absolutely continuous part, turns out that there is a function f such that this absolutely continuous part is given by the integration over the function f with respect to mu. And since it's a sign measure, it can only take one value plus minus infinity, so one part has to be in L1 at least, and if you have both parts in L1, then the measure is finite. Okay, so this function f is unique, almost everywhere, always identification almost everywhere. And the decomposition is also unique. So if you find another decomposition where you have two parts, one mutually singular, the other one absolutely continuous, then it has to agree. F is often called the Radon-Nikodym derivative, and sometimes we note it d nu d mu. I like this just because it's convenient. In some ways, in the notation, the d mu cancel. That's only notation. It doesn't really mean anything, the d. All right. So again, just to give you an example of a measure that is absolutely continuous with respect to another one, let's take the Lebesgue measure. And every time you integrate over a function, you get an absolutely continuous measure. So an important measure like that is the Gaussian measure. Let's call it mu, and it's given by integrating the Gaussian density. So that's my Radon-Nikodym derivative. You integrate over any set, measurable set A. Okay, so you can do that with any reasonable function f. So if you want to relate that to the Lebesgue-Stieltjes construction, this is a Lebesgue-Stieltjes measure, that is mu of AB is big FB big FA minus big FA. And what is my f here is just the integral from minus infinity to x of this density or Radon-Nikodym derivative. All right. Okay, so let's do the examples we did in class again. Here I recall you can the definition of mutually singular and absolutely continuous. So we'll assume we know what that means now. So let's start with a non-example. Let's say you don't have sigma finite. So the reference measure now is the counting measure. It's not sigma finite on 0, 1 and the Borel set of 0, 1. It would be sigma finite though if the set was countable, obviously. Okay, and my nu, it's a bit confusing maybe, but my nu here is the Lebesgue measure. And we have that the Lebesgue measure is absolutely continuous with respect to nu. Why? So that means that if I have a null set in nu, it has to be a null set in M. But the only null set of the counting measure is when you have 0 element, that is the empty set, and obviously M of the empty set is 0. So if it applied there the Radon-Nikodym theorem, then would have a Radon-Nikodym derivative, that is the measure M would be given by the integration over f with respect to the counting measure. But this is a sum. The integral with respect to counting measure is a sum. If it's over an uncountable set, it's a sum with uncountably many terms. And for this to converge, say for m of 0, 1, then f must be 0 in that most countable number of points. Otherwise, it's infinity. It's a simple exercise. So call B the set where f is strictly positive, the set is countable. So on one hand, if I restrict to B here, the integral, I don't lose anything because elsewhere it's 0, so I should get the same answer. But on the other hand, m of B, as Lebesgue measure is 0. Why? Well, a singleton always has Lebesgue measure 0. And if I take a countable union of the elements of B, then I get a sum, countable sum of 0, so it's 0. Okay? If I take, again, this is just a general fact, if I take a countable union of null sets, then this countable union is also a null set, just by sigma additivity. Okay, so that's for the non-examples, so it's good to go to a positive example where this applies. So let's take now RBRM as our reference space. M is the Lebesgue measure. And let's look at new Lebesgue measure constructing from this function. Okay, so anytime I have an increasing function, I can construct a measure, just f of b minus f of a, the usual. It extends to the whole Borel sets, Borel sigma algebra. So what's my function? So I take a linear function up to 0, then I jump at 1. At 0, I jump by 1, and then I go linear again. Okay. Now, every time you have a jump here, this is related to point mass. So the easiest example of a jump is the point mass, say, at 0, where the function, this is a measure, and what's the function f? It's 0 before 0, and it's 1 after 1. It has to be a right continuous, remember. This is related to the continuity of the probability. And so that's why the jump I put like this. Okay, so what's the measure of the set A for this point mass? Again, it's 1 is 0 in A, 0 otherwise. To see this, always go back to f of b minus f of a, right? If a, b contains 0, then I will jump by 1. And if a, b doesn't contain 0, then f of b minus f of a is 0. It's the same value. All right. So now what's my decomposition here? So I claim that actually delta 0 is absolutely continuous with respect to m. Again, to see this, I need to decompose R into two disjoint set. And on one, delta 0, must be 0. And on the other, m has to be also a 0 measure. And it's clear here that this decomposition would work because actually the point mass is only non-zero at 0. So I have a decomposition where m of 0 is 0 and delta 0 of r minus 0 is 0. So m lives on this set and the point mass lives on this set, supported on this set, we say. Okay, so that's my candidate for the decomposition. Maybe I should put it in red. This is the decomposition. It's unique, so if you found one, it's the right one. So why is that our decomposition? As we showed, these two are mutually singular, and obviously m is absolutely continuous with respect to m. And you can check, again, always looking at sets AB, that if I take the measure nu of AB, then it will be equal to the measure of AB of delta 0 plus the measure of AB of m. That's just an easy check, and it's kind of clear from the picture here. All right, so the Radon-Nikodym derivative in this case is simply 1, because this measure is obviously obtained by integrating 1 with respect to m. Okay, so now this raises an important question. So every time you have a jump, there's a point mass lying behind that for the Borel measures, and Lebesgue still just measure. So question, is that the only way to produce a measure that is absolutely continuous, singular, with respect to m? So another way to phrase this, are there Lebesgue just measure constructed from continuous function f that are mutually singular with respect to m? And the resounding answer is yes. Let's highlight this. Let's write this in red. Yes. And the perfect example is the Cantor function, canonical example. So recall how you construct the Cantor function. So the Cantor set, you start at the first step, you remove the middle third of 0, 1. So you remove that part. The red is not in the Cantor set, it's in the complement. And then I take the function I call f1, which is constant on that middle third, and then linear up to 1. Okay, I should say that here I go up to 1. Okay. Then in the second step, I keep that part, but I remove, okay, the middle third of the intervals that remained. So that's also in the complement of the Cantor set. Now what's my function? I make it constant on the complement of the Cantor set, and then linear on the Cantor set. So it looks like this. And you go on like this. So the next step, F3, would be removing the middle third of what's remaining. Remove that, put the function constant everywhere on the complement, and then do a linear function. So by construction, you get a sequence of continuous function. These are continuous, they are increasing, and they converge uniformly. That's a simple exercise. So therefore you have a limit, and this limit is a continuous function because the convergence is uniform. It's an increasing function, might be constant on the complement of the Cantor set. And so what's the measure? Again, let's call it the Cantor measure of any set AB is f of c of b minus f of a, where f of c is a Cantor function. Now, what's the decomposition for that Cantor measure? So we claim that the Cantor measure is singular with respect to M. Again, to see that, I need to find two sets that are disjoint. That gives me the whole set. Let's partition my set. And the Lebesgue measure has to be supported on one. It's going to be this one. And the Cantor measure has to be supported on another set, so that's C. To see that, so C is actually a null set. C is actually a null set for the Lebesgue measure. So we actually prove that. Okay, it's not hard to prove because this is a sequence. Cantor set is a sequence of decreasing set, and it's easy to see that if you remove the middle third, then the limit of the intersection will be 0. Now, for generalized Cantor set, where you remove a different fraction, then you might not have 0 here, but in this case it's 0. And the Lebesgue measure of the complement of the Cantor set is 0. Now, to see that, always go back to the generators, intervals A of B. So every time you have an interval A of B, for example, here containing the complement, then f of B minus f of A will be 0 because the function is constant on the complement. So same thing here, etc. So that measure is 0 on every generator, so it has to be 0 everywhere. It extends uniquely by Carité delivery. So you found a partition where the two measures are supported on each, and so therefore they're mutually singular, and so the decomposition is simply the Cantor measure plus 0, so the absolutely continuous part is 0, or if you wish, the Radon-Nikodym derivative is 0. Alright, so that gives you 3 nice examples. Okay, and there's plenty of others. Now, in the same PDF, I'll redo the proof of the Radon-Nikodym theorem. This is a bit of a strange proof. I won't do it in the video. You can look at it, but we'll see a better proof using the Riesz representation theorem, chapter 6, which is much more natural. So I invite you to look at it either in full in the PDF or the handwritten notes. And okay, so hopefully this video went well. Thanks.